So this is section 4.1, the areas and distance problems. And the first thing we're going to do is find the area under the curve of y equals x squared. So we know how to find the area of, say, a rectangle or a square or a circle. But now we're going to find the area under the curve of shapes that are not kind of normal to us, that we don't have formulas for. So when we think about y equals x squared, we know that, let's take a moment here to graph it. If you want, you can pause and think about what this is going to look like. Let's graph it from 0 to 1, since that's what we're trying to find the area underneath the curve of, from and to. So when we plug in, say, 0.25 or 1/4 to x squared, we're going to get 1 over 16. So I'm just going to kind of put that right here. If we take a half and we square it, we get a fourth. If we take 3/4 and we square it, we get 9/16. That's a little more than a half. And if we take 1 and we square it, we get 1. So we already know that this is a parabola, so we're just going to try to do the best we can to kind of create like that shape that is, kind of curvy. And then our job is to find out what is the area underneath this curve. But all we have so far is these shapes that we always know, like these, rectangle, square, circle. So what we're going to need to do is actually, we're going to start this section by approximating the area. So approximate the area. And what we do is we take the interval that we have from 0 to 1, and we're going to divide that interval into 4 equal subdivisions. So you might be able to see that we've already kind of started that. But we're just trying to find the area here from 0 to 1. So how much is that? Now you don't want to forget that you can actually kind of have a pretty good idea. You just have to think about the area of like each of these squares. That's one way to think about it. You can kind of estimate like how big, how much area in each square, and then maybe like, okay, half of it. You can always estimate, but we're going to be a little more formal here today. So the idea that we're going to be thinking about is the fact that we're going to sum it using the areas of rectangles. And so in order to do that, we're going to think about the rectangles in 2 ways. We're going to think about something called R4, and all R4 is 4 rectangles, that's the 4, coming from the right-hand side. So that means that the height of the rectangle is from the right-hand side of the interval. So the idea here is we're taking our interval, which is a length of 1 minus 0, and we're going to divide it into 4 equal subdivisions. And so that means that each rectangle is 0.25 wide. And you can see that from the picture that's how I've created this graph here so that you can see it. So let's first draw the rectangles for the right-hand side. So what it means is that you can see that we have four like subdivisions here. And then what we're going to do is we're going to create a rectangle by coming in from the right side of the interval. So it's going to start, we have 0, 0.25, 0.5, 0.75, and 1. And each rectangle is going to start from the right-hand side. So I'm going to start with 0.25, and then what I'm doing is this. And then I'm going to come to 0.5, and I'm going to do this. And then 0.75, try to make it as straight as possible, everyone. And then I have this, and then I'm also going to do it 1, and I have this. So first off, you should say, man, those rectangles are really going over that curve. I feel like if we find the area in these rectangles, it's going to be a pretty big amount of area. And you're right, this is only 4 rectangles. This is how we find them, but we do know the area of a rectangle, and that's what's important here. So in order to find R4, all we have to do here now is find the area of each rectangle. So if we take a look at the first rectangle, we can see that its width is 0.25, because it's 0.25 minus 0. And that's just 1/4. I'm going to put it as a fraction. And then the height of this rectangle, so think about the height being this right here, which is just the height of what happens when you put 0.25 into x squared. It's just a y value. And so we're going to have 1/4 squared. Then we're going to add the next rectangle, which again has that 1/4 width, but its height is the 0.5 or the 1/2 squared. And the next rectangle, again, width is always a fourth here, equal subdivisions. The height is that 0.75 squared. So we have that. And again, if you want to use the decimals, that's fine. And then the last one, 0.25, and then the height here is just, as you can see, just 1. Maybe I make an actual arrow. And it's just 1 squared. So it's really just literally finding the area of rectangles. In this case, kind of a width times a height, or a length times a height. Anything that you can say, it's, one side times the other side. That's all a rectangle is. And if we add that all together, we get 0.46875. You can check that if you want. And this is what's called the right-hand sum, because we are literally adding up the right-handed rectangles. We can do the same with the left-hand side. So you want to think about the fact that now every one of our rectangles would start, the height of it would be starting from the left-hand side. So for the left-hand side, it's still the same 4 intervals that we see, but now the height actually starts here. So I want you to see the first rectangle is going to have a height of 0. The second rectangle is going to have a height of what we get when we plug in 0.25, and then 0.5, and 0.75. So notice the difference. Definitely notice the difference in how much area we are adding compared to what we added the last time, because this is all we've got. So now there's really a small difference here. You can probably see it, that the first interval is 1/4, but its height is actually just 0. So notice that makes a big difference. And then if you see the next one is actually going to be the 1/4 squared. So you might kind of see the small difference here in the two. And we have 1/4, and then we have a 1/2 squared. And then we have a 1/4, and we have the 3/4 squared. So it's still just 4 rectangles. But notice that the right-hand sum includes the height of 1 times 0.25. And the left-hand sum does not include that, but includes 0 times 0.25. So if we add this together, we're going to get, you can say, do you think it should be larger than 0.4685, or do you think it's going to be less than that? If you have an idea of what's happening here, you probably picked up on the fact that it's going to be less. And so you can check this if you want. But we have 0.21875, and that's the left-hand sum. So depending on whether you come from the right or the left, just affects what the height of your rectangles are going to be. What you have probably noticed is that with the right-hand sum for this function, it's an overestimate. For the left-hand sum, it is an underestimate. So neither one is the exact value. They're both just approximations. So the little inequality you have there at the bottom should look like this. There you go, you have this. What we want to understand is that both of these are approximation, an under and an over, and that the true area underneath this function here is going to be somewhere greater than our left-hand sum and somewhere less than our right-hand sum. Somewhere in between. Now, if we ask the question, how do we make a better approximation? Most students will say, well, I would say more rectangles. So the smaller the width, you make your interval. So the number of rectangles that you have mean that you're going to be closer and closer to the function more times. And that's going to create a better approximation. So for example, I'll just tell you that if we were to do 40 rectangles, because you know we do not want to do that, but if we were to do 40 rectangles, we would have 0.32094. That would be our left-hand sum with 40 rectangles. And our right-hand sum would be 0.34594. And that would be the right-hand sum with 40 rectangles. And I'll show you one more here. Again, we are not going to do this, but if we were to do 4,000 rectangles, I want you to picture our 4,000 rectangles underneath that x squared curve. If we were to do 4,000, we'd have 0.3332. And then on the other side, we would have 0.33346. And that would be the right-hand sum with 4,000 rectangles underneath that x squared. And what you might be able to conjecture now, if you were to take a guess on what the actual area is under x squared from 0 to 1, you may be able to pick up on the fact that if we were to look at the limit's coming back, where n goes to infinity, where n is the number of rectangles, so as n gets bigger and bigger and bigger, and there's more and more and more rectangles, we have the right-hand side that's going to equal the left-hand side, and that's going to equal 1/3. So the true area under x squared from 0 to 1 is 1/3 if we look at the number of rectangles going to infinity, which is obviously a very big idea. So let's take a look at this general idea, which is let's let f be a continuous function. Gotta love those continuous functions. And for this one, let's let the function be greater than or equal to 0. So we have all our y values above the x-axis for all the x values on that interval a to b. We're going to subdivide that interval into n equal subdivisions. Okay, so who knows how many of the n's we're going to use. Let's let our first value be a sub x sub 0. So a is x sub 0. So that's essentially, us saying x sub 0 right here. And then, x sub 1, x sub 2. So these are just all the x values that are going to go along the bottom. So for example, the next one here is going to be x sub 1, and then x sub 2, and so on, all the way up to, x sub n. So it just depends on how many rectangles you have, what that value is going to be. So for the right-hand side, if you were to find, again, just generally speaking, if you were to find the right-hand side sum of this area, so you notice it's an approximation here, you'd be doing f of x sub 1, so you're finding the height, and then your width is going to be what's called delta x. And delta x is just the change in x. And that is simply, if you remember from the x squared problem, it's just in the x squared problem, 1 minus 0 divided by 4. In this case, just generally speaking, it's b minus a over n. So it's just the width of your interval divided by how many rectangles you're going to create, how many subdivisions you have. That's going to tell you the width of each of your intervals. And we call that delta x. And if we just continually find the area of all those rectangles, again, it is, you can do as many rectangles as you want. The more rectangles, the better the approximation. So we just add up all these rectangles. Notice they all have a change in x in them. Then you're going to get that's your approximation right there. You're adding up a bunch of rectangles. If you wanted to find the exact area, you would take the limit as n goes to infinity. And again, big idea there, but it would just be taking the limit of what we just did. And that's going to give you that exact area. So let's just, you get it, a whole bunch of rectangles in there. X sub n, delta x. Once we have that, again, this is my right-handed sum. That's going to be the limit as n goes to infinity of the right-handed sum. And that's going to give you the area underneath that curve, whatever it is. So now, suppose we know the velocity of an object, v of t, that's velocity at t, from a to b. Our question is, how far does that object go? And the key thing to remember is from way back is that distance equals rate times time, rate times time. And because we have that, understand that the bottom here is time and the y value here is rate. We have everything we need to find out how far the object goes, its distance. So the distance here is essentially just the change in x. And remember, that's on each rectangle. So you can just add it in the front if you want here, change in x, times, and then depending on whether you're going to do the right-hand sum or the left-hand sum, you would need your, let's say we're going to do like the left-handed side here, we would need the velocity at t being 0 plus the velocity at t of 1 plus the velocity at t2. Notice all of these are being multiplied by delta x because I moved it out, so they are all the area of rectangles. And then you would just continue that for as long as you needed to, depending on the function that you have, all the way up until the last rectangle that you need. So for this one here, what I want you to see, this example here that we have on the left-hand side, what you have above is a more general version. So the total distance, notice this one's kind of nice because we have a constant and then we have a linear function. So this is, the total distance here is just the area under the curve. And so because we have a rectangle, we can find the area of the rectangle. We also know what the area of a triangle is, so we can find that as well. So we'll do the triangle first since it's the first thing. So a triangle is 1/2 base times height. Notice that the base is 4, literally just 4. And the height here is 8. And then we would add to that the area of this rectangle. And we know the area of a rectangle is just its width here, which we can see is 4 to 10. So its width is 6 times its height, which is also 8. And then all we need to do is just have 32 times 1/2, which is 16. And then 6 times 8 is 48. And we just add the two together and we get 64. And notice this is a distance. So because we're doing meters per second times seconds, which you can put over 1 if you want, you should see that our final answer here is going to be meters. And just one more along the bottom, another example here. Estimate the distance traveled if a speedometer had the following reading. So this is a different problem than what we had above. We have the time in seconds, 0 seconds, 10 seconds, 20 seconds, 30 seconds, 40 seconds, 50 seconds, 60 seconds, and then how fast it is going at those seconds. So to do something similar, we just want to think about the fact that this is what we consider t of 0, t of 1, t of 2, 3, 4, 5, and 6. But notice it is changing over time, not necessarily linearly. All we have is some values. But in order to find this, we do want to understand that the change in time here for each of our intervals, like we had above, it was just 1 second. But here our change in t is 10 seconds. Okay. So if we wanted to do, say, a right-handed version, like a right-hand side for this, because you could estimate left-hand side, right-hand side, so we'll just estimate right-hand side, we would be taking that change in t, which is 10, and then we just be multiplying it, again, if it's the right-hand side, we just be multiplying it by the velocity at the different times. So it would be velocity at t being 1, plus the velocity at t being 2, plus the velocity at t being 3, and t being 4, and t being 5, and t being 6. And that's really all that it's going to be. So we just have to add, multiply 10 by, let me put it over here, 10 by whatever that number is. And I think I have that here, so you can do it if you want. Oh no, I actually, I have it a little bit differently, but it's fine. This is better. So if you add up all those values together, you should get 90. And that's going to give you, again, in this case, 900 meters, same sort of thing, meters over seconds times meters. So that would be the estimate of the total distance traveled. You could do the left-hand side as well. The only difference is instead of starting at T1, you'd start at T0 and go up to T5. Because again, you're thinking of it in terms of rectangles. And so you're either doing the left-hand side or the right-hand side. And that would be your answer for this one if you were estimating on the right-hand side.